This is Babitha, working as Assistant Professor in the Department of ECE in Institute of Aeronautical Engineering. In this session, I am going to discuss about problems related to the waveform generators. So, in the case of waveform generators, these are one of the applications of the operational amplifier. In the previous sessions, we have discussed the problems related to the differentiator, integrator, and the comparator, and inverting and non-inverting amplifiers, and different comparator circuits also. So now we'll see the problems related to the square wave generator as well as triangular wave generator. So the basic function of the square wave generator here is to generate the square wave signal from the given supply voltages. So here it is the free running oscillator. We are not providing any input signal here. Why? Because it is the oscillator circuit using positive feedback. So the circuit itself will generate the waveform whenever we'll provide the supply to that. And from the square wave generator, and we can able to generate the triangular wave generator also if we apply the output of the square wave generator to the input of the integrator, so that we can get the triangular wave generator or triangular wave signal. So while coming to the problems, the first problem is in the square wave oscillator shown. I'll show the figure. Calculate the frequency of oscillations if resistance R2 is 10 kilo ohms, resistance R1 is 8.6 kilo ohms, and the feedback resistance RF is 100 kilo ohms, and the capacitance value is 0.01 microfarads. So the given circuit in the problem is, it is the op amp with the inverting and non-inverting terminals. Okay, for the inverting terminal, the capacitor is connected and other end of the capacitor is grounded here, and they will measure the output signal V0, and the feedback resistance RF is also connected from output to input here. And for the non-inverting terminal, we have connected the potential divider circuit, that is two resistances R1 and R2. It is grounded here. So this is R2 and this is R1 resistance, and it is the 741 operational amplifier IC. So this is capacitance. So this is the circuit given in the problem itself. So from the problem, first we'll write the given data here. So the given data is the R2 resistance 10 kilo ohms and the R1 resistance 8.6 kilo ohms and the feedback resistance 100 kilo ohms and capacitance is 0.01 microfarads. So here we need to calculate the frequency of oscillation of this particular oscillator here. Okay, for the given oscillator circuit, at how much frequency it can able to generate the signal, at how much amount of frequency it can able to oscillate the signals, we have to calculate here. So this actually this given circuit is the stable multivibrator using operational amplifier, so that it is a square wave generator. We can say it as the square wave generator also, because in the stable multivibrator we don't have any stable states. So though it is the stable multivibrator, I am giving its time period is time period of this stable multivibrator is given by, that is T equal to 2 feedback resistance RF into logarithm of ln 2 R1 plus R2 divided by R2. Okay. So this time period is applicable if R1 resistance is 0.86 times the R2 resistance. Okay, whenever the R1 resistance is 0.86 times the R2 time, then only this time period is applicable here. Okay, so now we will substitute the values in this time period to find the frequency of oscillation. So here T equal to 2 into RF resistance value, here it is 100 kilo ohms, that is 100 into 10 power 3 ln 0.01 into 10 power minus 6 into 2 into R1 is 0.86 R2 plus R2 value I am keeping as it is divided by R2. Okay, so when we simplify this, we will get this value as 2 into 10 power minus 3 seconds. That is nothing but 2 milliseconds. T value we got here it as 2 milliseconds. So from this time period, we can able to find the frequency. Why? Because time is inversely proportional to the frequency. So from that I can write it as F equal to 1 by T here. So F equal to 1 by 2 into 10 power minus 3 will give it as 499.68 Hertz. So this is the frequency of oscillation for the given parameters of the stable multivibrator. So with the almost 500 Hertz frequency range of signals, it can able to generate from the given stable multivibrator circuit. So while coming to the second problem, for the circuit shown figure below, I'll show the figure now. If R2 equal to 100 kilo ohms, that is second resistance value is 100 kilo ohms, and the resistance R1 is 86 kilo ohms, and the positive saturation value is 15 volts, and the negative saturation value is minus 15 volts, and the feedback resistance is 100 kilo ohms, and the capacitance for the circuit is 0.1 microfarad. So from this we need to find upper threshold voltage VUT, lower threshold voltage VLT, and the frequency of oscillation F0. So before going to the problem, just I'll give the circuit which is given in the problem. So here op amp with inverting and non-inverting terminals, and the capacitor is connected to the inverting terminal, and the other end of the capacitor is grounded, and in the feedback RF resistance is connected, and for the non-inverting terminal, two resistances are connected here. This is V0 and here it is grounded. This is R2 resistance, this is R1 resistance, and this is capacitance. It is 741 IC, and it is plus VCC, and here it is minus VE for the circuit here. So for this circuit, we need to calculate upper lower threshold values as well as frequency of oscillation. So before going to the problem, just we will write the given parameters first. That is R2 resistance 100 kilo ohms, R1 resistance 86 kilo ohms, plus V saturation is plus 15 volts, minus V saturation is minus 15 volts, and the feedback resistance is 100 kilo ohms, and the capacitance value is 0.1 microfarads. So from this problem, we need to calculate VUT as well as VLT as well as F0, frequency of oscillations. These three parameters we need to calculate from the given circuit. So for that, to find the first bit, that is upper threshold voltage VUT, we know the formula. VUT, upper threshold voltage, is equal to R1 resistance into plus V saturation value divided by total resistances for the non-inverting terminal, R1 plus R2. So now substitute the values of resistances and saturation levels here. So R1 resistance value is 86 kilo ohms. So 86 into 10 power 3 into positive V saturation value is 15 volts. And the R1 resistance is 86 kilo ohms plus R2 is 100 kilo ohms. So after simplification, we will get this value as 6.94 volts. This is the upper threshold voltage of waveform generated from the given circuit. And to find the second parameter, that is B is VLT, lower threshold voltage. So to find that, we know the formula. V lower threshold voltage is equal to R1 into negative saturation level. Why? Because it is lower threshold value below the negative axis. Sorry, below the reference axis. So it is R1 into minus V saturation divided by total resistance. That is R1 value is 86 kilo ohms into minus 15 volts negative saturation level, and again R1 resistance value is 86 kilo ohms plus R2 resistance value is 100 kilo ohms. So if we simplify this, we'll get it as minus 6.94 volts. So this is the lower threshold voltage of the output waveform generated from the given circuit. And the third parameter we need to calculate here, it is frequency of oscillation. It is C equal to frequency of oscillations F0 is equal to, I am giving formula here, F0 equal to 1 by 2 RFC ln positive saturation minus lower threshold voltage divided by positive saturation minus upper threshold voltage. So this is the formula to find the frequency of oscillation here. So to find this value, just substitute all the values in the frequency of oscillation, that is 1 by 2 into RF value. Here it is 100 kilo ohms. RF value is 100 kilo ohms. And the capacitance value is 0.1 microfarads. Ln of positive saturation is plus 15 volts minus of minus 6.94. This is lower threshold voltage divided by 15 volts minus 6.94. It is the upper threshold voltage. So if we simplify this, one, we will get it as 1 by 0.02. So almost it is 50 Hertz. So frequency of oscillation required here, it is 50 Hertz for the given circuit. So while coming to the next problem, for the circuit shown in figure below, show that time period T equal to 2 times feedback resistance into capacitance whenever the R1 resistance is 0.86 times the R2 resistance. So to show T equal to 2 RFC, first of all, we have to know the circuit given in the problem. So for that, I am showing the circuit of the problem, that is op-amp with inverting and non-inverting terminals. And for the inverting terminal, the feedback resistance is connected from the output RF and also the capacitance C is connected, and for the non-inverting terminal R1 and R2 resistances are connected. So here we need to give the positive supply and here we need to give the negative supply for the circuit. So this is the circuit given in the problem itself, and here the given values are R1 equal to 0.86 R2. So we have to show here T equal to 2 times RF into C. So to prove that, here first of all we have to find the time period for the given circuit so that we can able to show that whether it is reaching the required condition or not. So for that purpose, I am finding the time period first, that is 2 RFC ln C ln plus V saturation minus of V lower threshold voltage and positive saturation minus upper threshold voltage. So this is the time period formula for the given circuit. Okay, so next we have to substitute the values of upper and lower threshold voltages and positive saturation, negative saturation values here. But to substitute the lower threshold voltage and upper threshold voltage, they didn't given in the problem and we are not able to find the values also. So that's why we have to substitute the formulas for upper threshold voltage as well as lower threshold voltage. So I am giving that upper and lower threshold voltage values. VUT, upper threshold voltage, is equal to minus R1 into minus V saturation divided by total resistance of the non-inverting terminal. And similarly, lower threshold voltage VLT equal to minus R1 into plus V saturation divided by total resistances of the non-inverting terminal R1 and R2. So now this one, take it as the first equation and this one is second and third equations. Now substitute two and three equations in first one or first equation. So if we substitute that lower threshold voltage as well as upper threshold voltage in the time period equation, we will get it as 2 RFC ln plus V sat minus of R1 into minus of V saturation divided by R1 plus R2 and minus V saturation minus of R1 into plus V saturation whole divided by R1 plus R2. Okay. So here suppose the magnitude of positive saturation level as well as the negative saturation levels are equal, this total term we can simplify as to, if both the magnitudes are equal only, we can simplify it as T equal to 2 RFC ln plus V saturation of 1 plus R1 by R1 plus R2 divided by plus V saturation of 1 minus R1 by R1 plus R2. And I have already mentioned this is applicable whenever both the magnitudes of upper and lower threshold voltages are same. So now we can again simplify it as 2 RFC ln plus 2R1 plus R2 by R1 plus R2 overall divided by 2R1 R2 by R1 plus R2. So again, if we simplify this, we will get it as 2RFC ln 2R1 plus R2 by R2. So in the problem, they given the condition whenever R1 is equal to 0.86 times the R2 resistance. So the same condition I am applying in the fourth equation. Substituting fourth equation. So now T equal to 2 RFC ln 2 into 0.86 R2. In the place of R1, I am writing it as 0.86 into R2 plus R2 divided by R2. So 2 RFC ln this total value we will get it as 2.72. Okay, and 2 RFC ln 2.72 value we will get it as almost 1. So T equal to 2 RFC. See, whenever if we take the R1 resistance value as 0.86 times the R2 resistance, we are reaching the condition T equal to 2 RF into C here. So the given condition is correct here. We have proved from this relation by using the given circuit diagram. So while coming to the next problem, for the circuit shown in figure below, I am showing the figure first. That is for the inverting terminal, one capacitor is connected and feedback is one resistance is connected and other end of the capacitor is grounded, and here two resistances R1 and R2 are connected to the non-inverting terminal. Okay, so this is the circuit given in the problem itself. Okay, below, if resistance R2 is 200 kilo ohms, R1 is 96 kilo ohms, positive saturation level is 15 volts and the negative saturation level is minus 15 volts, and the feedback resistance is 200 kilo ohms, and the capacitance value is 0.1 microfarad. And in this case also, we need to find the upper and lower threshold values as well as frequency of oscillations. So the given values are R2 equal to 200 kilo ohms, R1 equal to 96 kilo ohms, plus Vsat equal to plus 15 volts, minus saturation level equal to minus 15 volts, and the feedback resistance value is 200 kilo ohms, and the capacitance value is 0.1 microfarad. So we need to find VUT how much and VLT how much and what is the frequency of oscillation. So for this purpose, we need to know the formulas for upper threshold voltage, lower threshold voltage as well as frequency of oscillation. So while coming to the first bit in the problem, that is upper threshold voltage. So the formula for upper threshold voltage I have already mentioned, that is R1 into plus Vsat divided by total resistances for the non-inverting terminal. Those are providing the positive feedback. Okay, substitute the values of all the resistances and saturation voltage values here. That is 96 into 10 power 3 R1 value is, and into positive saturation value given in the problem is 15 volts, and again R1 resistance is 96 kilo ohms and the R2 resistance value is 200 kiloohms. So we will get here it as 1440 into 10 power 3 divided by 296 into 10 power 3. So after simplification, we will get it as 4.86 volts. So this is the upper threshold voltage value for the given circuit. And similarly, we need to find the lower threshold voltage, VLT. So VLT is equal to R1 into negative saturation value divided by total resistances R1 and R2. So substitute the values of R1, R2 resistances as well as positive saturation value. So R1 resistance is 96 into 10 power 3 into minus 15 divided by 96 into 10 power 3 plus 200 into 10 power 3. So it is again minus 1440 into 10 power 3 divided by 296 into 10 power 3. So we will get it as minus 4.86. So this is the value of lower threshold voltage for the given circuit. And next, we need to find the frequency of oscillation here. That is the third bit, F0. So to find the frequency of oscillation, we know the formula. F0 equal to 1 by 2 RFC ln plus V saturation of minus V lower threshold voltage divided by plus V saturation of minus V upper threshold voltage. Now substitute the values here. 1 by 2 into feedback resistance is 200 kiloohms. And the capacitance value is 0.1 microfarads. Ln positive saturation value is plus 15. And the lower threshold voltage is minus 4.86. And positive saturation is 15 minus upper threshold voltage is 4.86. So we will get it as 1 by 40 into 10 power 3 ln 19.86 divided by 10.14. So if we simplify this, we will get it as 1 by 40 into 10 power minus 3 ln 1.958. So it is 1 by 40 into 10 power minus 3 ln 1.958 value is 0.6719. So if we multiply these two values in the denominator, we will get it as 26.87 into 10 power minus 3. So if we simplify this, we will get it as 37.2 Hz. So this is the value of frequency of oscillations. So in this way, in the case of waveform generators, we can able to find the time period as well as frequency of oscillations and the positive as well as negative saturation values, and from that we can able to find the upper threshold voltage as well as lower threshold voltages. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.